So a couple lessons ago we learned all about the basic parameters of pipe flow. One of the things we learned is that if the Reynolds number is bigger than 4,000, then we expect the flow to be turbulent. To find the head loss, I like to go through the procedure to find the Reynolds number, find the value of F, and then find the head loss. We did that for the laminar case last lesson. In this case, the only difference is instead of using the formula for F that we saw last time, we need a new formula for F. So for turbulent flow in a smooth pipe, we have this formula for F. 1 over the square root of F is 2 times the log base 10 Reynolds number times F minus 0.8. Now a couple things about this equation. First of all, it's only for smooth pipes, so we'll get to what that means in a minute. The other thing you may notice is that it's a much more complicated equation than what we had for the Reynolds number. Not only is it longer, there's also F's on both sides, which is going to pose a different sort of problem, as we're going to see. So first question, what do we mean by smooth? So if you look at the pipe walls on the inside of my pipe, whatever the material is going to have some level of surface imperfection. So what we do is we set up a new parameter, epsilon, which is called the equivalent wall roughness. This is basically a measure of how high those surface imperfections are, so how high these little bumps go into the flow. So if epsilon equals 0, the height of those bumps is 0, so the pipe is nice and smooth. The bigger the value of epsilon, the more rough the pipe is. That's obviously going to depend on the material. Some material is smoother than others. Plastic is pretty smooth. Concrete is fairly bumpy. So smooth, plastic is going to have the epsilon value of 0, meaning it's smooth. Concrete is going to have a relatively high value of epsilon. Again, you find all the values, table 12.1. And then this leads to a new non-dimensional parameter called the relative roughness, epsilon over d. So if you remember the previous formula we had for F, only depended on one non-dimensional parameter, the Reynolds number. Now that we have this guy as well, we need a new formula involving both of these parameters, the Reynolds number and this relative roughness. So this leads to a new equation for our parameter F. 1 over the square root of F is negative 2.0 log base 10 epsilon over d over 3.7. That's our new parameter, plus 2.51 over Reynolds number times the square root of F. So it looks kind of similar, and actually if epsilon equals 0, plug that into this formula, we get the same formula we had before. So this works no matter what, whether the pipe's smooth or not. So question now is, again, I have an F on the left-hand side, have an F on the right-hand side. So how do I actually solve this for F? It turns out there are 3 options. So the first option we have is the most time-consuming, also probably the most accurate. So using this equation, we can iterate, in other words, guess a value of F. A good value to start with is roughly 0.02. That's generally a good middle ground of what the value of F is going to be. So starting with that number, plug into the right-hand side, whatever the epsilon over d value is, plug all that in. It's going to give me a number. I can solve for that number. Gives me a new value of F. If that new value of F is the same as the old value of F, then I can go with it. If it's not, I want to take that new value of F and repeat the process, so plug it back in the right-hand side, get a new value for F, and then keep on repeating that procedure until the 2 F values are the same, and that's the one I'm going to use. Second option is a lot quicker, but it's only approximate, and that's an approximate formula that's been derived based on this first more complicated one. At an approximate formula, F equals 0.25 over log base 10 epsilon over d plus 5.74 over Reynolds number to the 0.9 power. Take that whole thing on the bottom and square it, and that gives you an approximation for F. So nice thing about this one is there's no F on the right-hand side. Just straight up plug all the numbers on the right-hand side. Gives you an approximate value for F. And then the third option is something called the Moody chart. Again, it's going to be relatively fast, but also not quite as accurate. Basically what the Moody chart is this equation plotted for a whole bunch of epsilon over d values. So you have a whole bunch of lines corresponding to different values of epsilon over d. And then x-axis is the Reynolds number, y-axis is the value for F. So you have some epsilon over d, You find what line you want to be on, find the Reynolds number, X value, and then you can go up to that line and go over to the Y axis, and that'll give you the value for F. So here's the Moody chart. Again, it's a plot of that previous function for a bunch of different values of epsilon over d. So you can see each black line on the right hand axis has a value for epsilon over d. And then again, have Reynolds numbers on the x-axis, f values on the y-axis. So find the appropriate line based on epsilon over d. Find the appropriate Reynolds number on the x-axis, where those numbers or those lines intersect. Go over to the y-axis, and that's your value of f. So generally, there are three types of problems dealing with pipe flow. The first of which is to find the head loss in a system. So this is the standard procedure we've seen before. Find the Reynolds number, then find the value of f, then find the head loss. The second is if you want to find the flow rate, so you have a bunch of stuff going on. You know what the pressure difference is, you know some other things going on, and want to know how fast is water actually going to flow out of your pipe. And then the third type of problem is called the design problem. Basically, again, you know all these parameters, you know what kind of flow rate you want, you know what kind of head loss you're going to be generating. And you want to find what diameter of pipe is going to accomplish those goals. So what we're going to do now is see an example, one of each of these types of problems. And you're going to see the first one is relatively simple. The next two get a bit more complicated. Maybe we'll see why. If not, we'll get to it when we do the examples. So first example, we have some water, 50 degrees Fahrenheit, flowing through a 6-inch diameter asphalted cast iron pipe, flow rate of 0.5 cubic feet per second. Want to know what the head loss is per mile of pipe. So again, type 1 problem, find the head loss. So solution to this, going through the standard procedure. First thing to do is find the Reynolds number based on diameter. So Reynolds number is density, velocity, diameter over viscosity, or velocity, diameter over kinematic viscosity. I wasn't given a velocity, I was given a flow rate, so I can change that velocity to Q over A, flow rate divided by area, then area is pi d squared over 4. So that brings me down to Reynolds number of 4 times Q over pi d times kinematic viscosity. So I'll look that up in the back of the book for water at 50 degrees Fahrenheit. End up with 1.41 times 10 to the negative 5 feet squared per second, diameter of 6 inches, half a foot, pi, flow rate 0.5 cubic feet per second, gives me a Reynolds number of 90,300. The next step, I want to find the value for f. So to find the value of f, I need epsilon over d. So I need epsilon for an asphalted cast iron pipe. I can look that up in the table. Epsilon is 0.005 inches. So epsilon over d, 0.005 inches over the diameter of 6 inches, gives me 0.000833. Beware of the units here, usually given in inches, so you want your diameter in inches as well. And then I can use either equation, so I can either iterate or use the approximate equation or look at the Moody chart, and either way should end up with an f value that's 0.022, or at least close to that. And then finally find the head loss. So standard formula for head loss, HL, F, L over D, V squared over 2G. But again, I have a flow rate, don't have velocity, so I can change my V to Q over A, same as did before. I get the head loss is F, 8LQ squared over pi squared, G d to the 5th power. So plugging all those numbers in, F I found was 0.022, 8 a mile is 5280 feet, flow rate 0.5 feet cubed per second, square that guy, pi squared, G value 32.2 feet per second squared, then my diameter 0.5 feet to the 5th power, gives me a head loss of 23.4 feet for this scenario. So here is the Moody chart for that previous example. We have an epsilon over d value of 0.000833. Now there's no specific line on this Moody chart for that specific epsilon over d value, so it's going to be somewhere between the 0.0005 and the 0.001 values. So roughly where that line is given by a new blue line. So draw a little blue line in there, roughly where that should be. Then a Reynolds number of 90,000, just over 9 times 10 to the 4th. So purple line on my x-axis, go up where that intersects my new blue line, and then go over across the green line to find my f value, And you can see there it's roughly 0.022 like we had in the example. So my second example, I have water in a tank, 20 meters high, flowing through a steel pipe, 50 centimeter diameter. So 100 meters of steel pipe with 50 centimeter diameter. I want to know what the discharge is coming out of this pipe. So how fast is water flowing out of my pipe down here? So type 2 problem, want to find the discharge. So first thing for this guy, I'm going to look up some important parameters for the problem. So for water, I'm going to need to know its kinematic viscosity. That's 1.0 times 10 to the negative 6 meters squared per second. Pipe's made out of steel, so we're going to need to know the roughness parameter for that. So epsilon 0.045 millimeters. And now I can actually start to solve this problem mathematically. So we're going to start with Bernoulli's equation, have some elevations and pressures, things of that nature. So that's a good place to start here. So with Bernoulli's equation, P1 over gamma is V1 squared over 2G plus Z1 plus pump gain equals same thing at point 2, P2 over gamma, V2 squared over 2G, Z2, and my head loss. Now points 1 and point 2, I want to pick those where I know the most amount of things. So I'm going to pick point 1 to be at the top of my tank. I know the pressure, I know velocities, things of that nature there. Point 2 is where I want to know basically V2 is what I'm trying to find, because I can relate V2 to my flow rate Q. So from this, I'm going to try to find V2. So with those points, I can see that I have atmospheric pressure acting on the top of my tank. Tank's open, so atmospheric pressure up there. This pipe is exiting again to atmospheric pressure. So P1 and P2 are both atmospheric pressure. So because they're the same, I can cancel those guys out. And then V1, my velocity at the top of my tank. So again, I'm assuming this tank's really big compared to this 50 centimeter diameter pipe. So if this tank is really big, this water's going to go down really slowly compared to how fast it's coming out. So V1, approximately 0. Can get rid of that guy. And then I'm going to set my elevation, Z2, to be 0. So if Z2 is 0, it means that Z1 is 20 meters. But more importantly, Z2 is going to go away. Keep Z1. And then last thing, there's no pump here. This water is being pushed out through the pipe, basically just through gravity itself. So there's no pump, nothing else needed to actually pump it through the pipe. So HP being 0, I'm left with that equation there. So what's left over in that equation, Z1 equals V2 squared over 2G plus my head loss. Head loss I know is FL over D, V2 squared over 2G. So again, my head loss is in this pipe. Velocity there is going to be V2 because conservation of mass. Whatever's coming out of my pipe has to be going in, so the entire velocity through my pipe is V2. I can actually take a V2 squared over 2G out of that whole thing and left with 1 plus FL over D. I'm looking for V2, or my flow rate, so solve that equation for V2. Using that V2 is the square root, 2G times Z1 over 1 plus FL over D. Only thing I don't know in this equation is F, so now just find F. So to find F, first thing I do is find the Reynolds number. Reynolds number, velocity, diameter over kinematic viscosity. Velocity of my pipe, as I said, is V2, but V2 is what I'm trying to find. So I don't know V2. So how do I do this? And so the answer to that is to iterate, so much like we did to find F using the full equation. Guess the value for F, plug it in, see what that gets you, check to see if it's right or not, and keep on going until those values are the same. In this case, what we're doing is we're iterating for V2, so I'm going to guess the value of F, plug it in, find a value for V2. Once I do that, I'll check to see whether that value of V2 gives me the same value of F. Then if it does, I'm good. If not, I'll have to do it again. So that's why this example is a little bit harder than the last one. So doing that, guess the value of F, 0.02, plug that into my equation up here. So 2 times G, 9.81, Z1 is 20 meters, then 1 plus F, my guess value 0.02, length of the pipe of 100 meters, diameter 0.5 meters, gives me a first approximation for my velocity of V2. Now I need to see whether that V2 gives me the same value of F that I guessed. So again, to check to see whether that's the same value of F or not, plug it into my Reynolds number. So velocity 8.86 meters per second diameter 0.5 meters, kinematic viscosity of water 1 times 10 to the negative 6 meters squared per second. Then to find F, I also need to know epsilon over D. So epsilon was 0.045 millimeters. Diameter here in millimeters is 500. Gives me epsilon over D as 9 times 10 to the negative 5. And so plugging that into the equations or the Moody chart, whatever you want to do, get an F value of 0.012. This is not the same as the value that I guessed, 0.02. So you need to do this again. So use this 0.012 as my new guess. So plugging this back into my equation for V2 with all the other parameters being the same. So G is still 9.81 meters per second squared. C1 still 20 meters. Length still 100. Diameter still 0.5. Gives me a new velocity of 10.7 meters per second. So the only thing that changed is my value for F. 10.7 meters per second. Don't know if that's right or not, so I need to plug it back in to find F using that new value for velocity. So Reynolds number, 10.7 meters per second, 0.5 meters of diameter. Kinematic viscosity, 1 times 10 to the negative 6 again. New Reynolds number of 5.37 times 10 to the 6th. Epsilon over D stays the same, 9.0 times 10 to the negative 5. So with these two values, again, equation, Moody chart, whatever you want to use, gives me an F value of 0.012, which is the same as what we had before. So because it's the same as before, we know that's the right answer, that's the right value for F. Because that's the right value for F, this is the right value for V. So my V2 is in fact 10.7 meters per second in this case. Now, not quite done yet because we're trying to find the flow rate, the discharge. But now that we know V2, just take that velocity multiplied by the area of the pipe to give us Q. So velocity times pi d squared over 4, so 10.7 meters per second, pi over 4, 0.5 meters squared, gives a flow rate or discharge of 2.1 meters cubed per second. So last example, want to know what size of concrete pipe. By size I mean diameter. This concrete pipe has an epsilon value of 0.05 inches. So what size diameter do I need to carry gasoline at a flow rate of 3 cubic feet per second and with a head loss of 4 feet per 1,000 foot of pipe? So to solve this guy, I know the head loss is F times L over D times V squared over 2G. But again here we have a flow rate, a Q, instead of a velocity V. So I can change that. V is Q over A again. So that gives me that head loss is F times 8L Q squared over pi squared G, D to the 5th power. Since I want to know the diameter, I can solve that for D. So move that over, take the 5th root at 8FL Q squared over pi squared G HL to 1/5 power. Gives me D. In this expression, I know everything except for F. So I want to find F now. To find F, I find the Reynolds number. So Reynolds number, BD over nu. But again, I want that in terms of flow rate. So 4Q over pi times nu times the diameter. Diameter is what I'm trying to find. So can't do that. So similar to the last example, need to iterate. So standard iteration procedure, guess the value of F. Going to guess 0.02. I'll plug that into my expression for D. So 8 times 0.02, length of 1,000 feet, Q, 3 feet cubed per second, square that, pi squared on the bottom, 32.2 for G, and then my head loss of 4 feet. All the 1/5 power gives me a first guess of the diameter of 1.03 feet. Now I want to check to see if that's right or not. So find a new F value based on that diameter. So Reynolds number, 4Q over pi nu times D. So 4 times 3 feet cubed per second, pi. Nu, kinematic viscosity for gasoline, you need to look that up. Back of the book in the table, find 4.9 times 10 to the negative 6 feet squared per second for that guy. And then this guess of the diameter, 1.03 feet. Gives a Reynolds number of 760,000. Then epsilon over D, epsilon for my concrete 0.05 inches, diameter 1.03 feet. I can want that in inches, so multiply that by 12. Gives me epsilon over D of 0.00405. So with that Reynolds number, that value of epsilon over D, you can find F to be 0.029. That's different than 0.02. So you get to do this all over again. So repeating the whole procedure, F is now 0.029. Only thing changes in my diameter equation is this value from 0.02 to 0.029. Gives me a new diameter of 1.1 feet. Now to check that guy, plug in the Reynolds number. Again, the only thing that changes is my diameter, 1.1 feet. Gives me a new Reynolds number of 709,000. In this case, I have a new value of epsilon over d as well, because d changes. So my new value of d, 1.1 feet, again times 12 inches per foot, gives me epsilon over d of 0.038. Again, plugging those guys into the equations or into the Moody chart gives you a new f value of 0.028, which is very, very close to the old one, but not quite the same. So one more time. So 0.028 now for value of f. Again, that's the only thing that changes. Still gives me a diameter of 1.1 feet. So because it's the same number as before, the rest of it's the same as before. Back to 0.028 for f, and we are finally done. So the diameter of pipe that we want is 1.1 feet.